Welcome back as we plunge into the thicket of Gaussian Elimination Endgames. I introduced you to Gaussian elimination itself in the last video, and I want to begin with a quick recapitulation of a typical example. If you need more detail, please do revisit that previous video. The idea was we begin with a system of linear equations, and Gaussian elimination is the technique we use to find the system's solutions. We begin by rewriting the system in linear algebraic terms. The whole system could be expressed in the form ax is equal to b, like so. And this gives us a more dynamic picture of the system. But we also saw that we can pack all the relevant information in this equation into an augmented matrix. And that is the object on which we perform our Gaussian elimination. You will recall that Gaussian elimination is a process involving three so-called row operations, three ways to transform the rows of our matrix. And of course, when we change the numbers in the rows, we change the underlying system of equations. But, the three row operations are designed so that even though we are changing the system of equations as we make each move, the set of solutions to those equations remains constant. It's as if we're only making changes somehow to the exterior, while the interior, the set of solutions to the linear system, remains untouched. And the idea is that the Gaussian elimination, the sequence of row operations we make, simply exposes that interior so that we end up staring right at the solution to the system. Anyway, let's carry it out on this particular augmented matrix as a quick reminder of what the three row operations are and how we typically deploy them. So the first thing we would like to do in Gaussian elimination is to get a 1 up in this top left corner. We can do that here by using the first of our three row operations, which is to swap two rows. Namely, let's swap rows 1 and 2. And I'll put a little chicken scratch here to remind myself of what I did. Okay, so that's the first of the three row operations. We can swap rows. The second row operation is that we can scale a row. And to remind you how that works, I'm going to go ahead and scale this second row just to clean things up, since every number in this row is a multiple of 3. So if I scale that second row by 1/3, it becomes 1, 3, minus 2, and 5, and the other two rows come over unchanged. So now we've reviewed 2 of the 3 row operations. Before I move on to the third one, I'll note that we could have, going back to the beginning, managed to get a 1 in that upper left corner by scaling the first row by 1/3, and that would have been fine too. The third row operation is where we add or subtract a scaled version of one row to another. And this is the operation we do to achieve the elimination part of Gaussian elimination. Namely, once we get one of our wonderful 1s in just the right spot, we use that third row operation to eliminate all the non-zero entries below it. And very often we like to eliminate any non-zero entries above it as well. So we zero out the whole column except for the magical 1. Eliminating everything below the 1, below the so-called pivot, helps bring us to row echelon form. And eliminating everything above the 1, if there is anything, obviously there isn't in the first column, helps bring us to what we call reduced row echelon form. But let's see it in action. Here's my pivot. I will use it to zero out the rest of its column. First, I'll do a row operation on the second row. What I'm going to do is to subtract row 1, which turns this row into this row. Now I want to turn this 2 into a 0. To accomplish that, I can't just subtract row 1, because then I'd have 2 minus 1 is 1. I must subtract 2 copies of row 1. And when I subtract 2 copies of row 1 from this third row, I end up with this stuff. Okay, we have successfully zeroed out everything below that first pivot. Let me make a little more room for myself. That's much nicer. And we will continue the elimination. The trick now is to get one of our magical 1s, one of our pivots, in row 2, column 2, continuing on down that main diagonal. Well, it's easy to see how to do that. We can just scale the second row by minus 1/2, which gives us this. And from here, we want to use that pivot to eliminate everything above and below it, zeroing out that second column. And we do that in the obvious way. To get rid of the 5 above it, we're going to take that first row and subtract 5 copies of row 2. giving us this stuff. And to get rid of the -6 below our pivot, we're going to add 6 copies of row 2, which gives us this. And if we want, we could stop here because we have achieved row echelon form. And to be in row echelon form, 2 things have to happen. First, any 0 rows, in other words, rows consisting entirely of zeros, must be at the bottom. Well, there are no 0 rows here, so this first requirement is satisfied in a vacuous sense. As for the second, more substantial requirement, in the rest of the rows, in other words, the non-zero rows, the first non-zero entry, that's what we call the pivot in that row, must lie to the right of the pivots of any rows there are above it. And that's what we have here. Let's check just to be clear. We look at each of our non-zero rows, that's all of them, and in each one I've circled my pivot, the first non-zero entry. Well, this one, the 3, is definitely to the right of both of the pivots in the rows above it. And similarly, this one, the one in the middle, lies to the right of the 1 pivot that lies in a row above it. And for the pivot in the top left corner, well, there are no rows above it, so the condition is satisfied, again, in a vacuous sense. So yes, this one is in row echelon form, unlike all the preceding ones, which are not. And this second condition is a mouthful, there's no question about it, and it's not the kind of thing one memorizes. For the most part, row echelon form is something you just recognize when you see it. And as I mentioned briefly in the last video, the echelon is a kind of staircase of zeros, like the one I've just drawn in here. We don't really have that in any of the previous matrices. And it is precisely that second condition for row echelon form that ensures that we have that echelon, that staircase. It ensures that there are only zeros below each pivot. But the point of all this is that whenever we achieve row echelon form, we can solve the underlying system by backward substitution. And I'll quickly show you what I mean to remind you. If we take our augmented matrix in row echelon form and extract the underlying system of equations, we can solve this through that back substitution process by beginning at the bottom and working our way up. So in this case, the bottom equation says 3z is 6, which tells us immediately that z must be 2. But if z is 2, I can substitute that into this middle equation, turning it into y minus 6 is 2, and therefore y is equal to 8. So now I know what z and y are, which means I can take those values and pop them in the first equation and discover the value of x. And lo and behold, I have my unique solution to the original system of equations, which we achieved by turning the system into an augmented matrix, performing Gaussian elimination until we reached row echelon form, extracting the corresponding equations, and solving those by back substitution. However, we could have reached this by a slightly different path if we did not stop at mere row echelon form and instead pushed on to reduced row echelon form. For a matrix to be in reduced row echelon form, or RREF as we often abbreviate it, a few things have to happen. 1, it has to be in row echelon form, not surprisingly since row echelon form is part of the name. But there's more on top of it. 2, all the pivots must be 1s, so not like this one where we had a 3. And 3, all entries below and above the pivots must be zeros. In mere row echelon form, all the entries below the pivots are zeros because of that staircase of zeros. But in reduced row echelon form, we want all entries above the pivots to be zeroed out as well. Anyway, let me make a little more room here for myself. Good. And now let's continue boiling this matrix in row echelon form all the way down to reduced row echelon form. The first thing we will need to do to meet this second condition is to turn this 3 into a 1, which I can do very easily by scaling the third row by 1/3, which will turn it into this. Good. Now all the pivots are 1s, and all we have to do is zero out this third column. Okay, and that's easy enough. We'll just need to add or subtract a certain number of copies of that third row from the first 2. In particular, to turn that -3 into a 0, we're going to need to add 3 copies of row 3, which yields this, and to turn that 7 into a 0, we will need to subtract 7 copies of row 3, which gives us this. And now we're done. This matrix is in reduced row echelon form. It's boiled down as far as it will go. There's a few nice things about reduced row echelon form. One is that it's unique. Every matrix has one and only one reduced row echelon form, whereas it can have many different row echelon forms. After all, this one and this one are both row echelon forms, but only this one is reduced. That uniqueness is nice in the theory of linear algebra, because we can talk about the reduced row echelon form of a matrix. It's like a kind of skeleton of the matrix. The other really nice thing about reduced row echelon form is that we can read the solutions of the system off immediately. There's no need for back substitution or anything like that, because if we think about the underlying system of equations corresponding to that thing, well, those equations are x equals minus 15, y equals 8, and z equals 2. So those are the coordinates of the unique solution to our original system of equations. Pop those values into those equations, and in all three cases, you will get a true statement. Now, my experience is that most students get pretty excited about reduced row echelon form and say, well, let's always go to that because it always hands you the solutions on a silver platter. And indeed, that is mostly what we'll be doing in this book. But there are good reasons for frequently in practice, when we're actually computing something, stopping at ordinary row echelon form and then using back substitution to get the solutions. From a computational standpoint, I mean, from a computer science standpoint, solving a system by going to row echelon form and then doing back substitution is much more computationally efficient than going all the way to reduced row echelon form. Because, at least for large matrices, just going to row echelon form and then doing back substitution involves fewer individual computations, say only half as many as it would to go all the way to reduced row echelon form. Consequently, if we just go to row echelon form, a computer can carry those operations out much more quickly, say in half the time, and nobody wants a sluggish computer program. You now have, I think, the basic flavor of how Gaussian elimination works, how we use those three row operations to push an augmented matrix all the way down to reduced row echelon form, or at least row echelon form. You can, of course, write down a specific algorithm, a kind of flowchart of steps for carrying Gaussian elimination out. I don't think this is helpful at all for human consumption, although I have such an algorithm written in the book. It's worth looking at, but for the most part, you can just follow your nose and you end up getting where you intend to go. But if you're training a computer to do Gaussian elimination, you can't just tell it, follow your nose. You have to actually program exactly what it needs to do, and that is what the full algorithm would do for you. So see the book for full details on that. What I want to spend the bulk of this video on are what I'm calling Gaussian elimination endgames, the kinds of things that can turn up towards the end when you are doing Gaussian elimination. Like the example we did here, which was very much like the example we did in the previous video. We had a system of three linear equations in three unknowns, and as we saw last time, we normally expect to see a unique solution in systems of that form, and indeed we got one. And in both cases, when we went to reduced row echelon form, we ended up with a copy of the identity matrix on the left of our vertical line, and the solutions were on the right. But it doesn't always work out that way, and sometimes it can't. After all, the identity matrix is a square matrix, and there's no reason why we have to have as many equations as we do unknowns, and therefore no reason why we have to have a square matrix on the left side of that vertical line. So instead of doing example after example where I write down a system of linear equations and turn it into an augmented matrix and carry out every nasty step of the Gaussian elimination, and then finally get it into a form where we can read off the solutions, instead of doing that, which is so time-consuming over and over and over again, I'm just going to cut to the endgames and say something like, here is an augmented matrix in reduced row echelon form, right? Here are the pivots, only zeros above and below, and we don't have to worry about putting 0 rows at the bottom because there aren't any 0 rows. Anyway, here is an augmented matrix in reduced row echelon form. It presumably was obtained by boiling down some other augmented matrix via Gaussian elimination. But we are going to skip all of that tedium and just start here at the endgame and ask, what can we say about the solutions to the underlying system? This looks a little different from the ones we've done before, because this corresponds to a system of 2 equations in 3 unknowns. And we know that such systems usually have infinitely many solutions. So let's see what's going on in this case. It's already in reduced row echelon form. So let's go ahead and extract the system of linear equations, which would look like this. This isn't as simple as the ones we've done before. I mean, the second equation is very promising. It tells us that y has to be 2 for any solution to the underlying system. But now we don't have specific values for x and z. We just have this relationship that x and z must satisfy, which makes sense if we're going to have infinitely many solutions. What this is all telling us is that for all of those infinitely many solutions, the second coordinate, y, will be 2, but x and z could be all sorts of things. It's just that together they have to satisfy this relationship, which means that once we know either x or z for any particular solution, then we don't have any choice in the matter about the other one. And we can see that more clearly in this, and indeed in any situation like this, if we follow the usual convention, which is to keep the leading variable and then move any other ones over to the other side, so that we end up rewriting that in this form. X is 1 plus 3z and y is 2. And from this expression, we could write down all sorts of individual solutions. For example, some solutions would be, well, let's make up a point, an ordered triplet that would satisfy this. We know the second coordinate has to be 2. And the way we've written this first equation, we have x as a function of z. So if I tell you what z is, and I could let z be anything I like let's say z is going to be 0, then I have no choice in the matter of what x is. X has to be 1 plus triple that value of z. So in this case, that would be 1. So this point is a solution to the underlying system. It's not the only solution. After all, we could have another one where, well, y has to be 2, but let's say our z value is, 14. What's the x value that would have to correspond to it? Well, this equation tells us. We triple the 14, which gives us 42, and then add 1, and we get 43. These values of x, y, and z satisfy the system, so they're solutions to the original system, because the process of Gaussian elimination preserves solutions. Great, so now we've got at least 2 solutions, and you can find as many as you like. For example, we could have y as 2, z as 1/3, and then x would have to be 2, and so on and so forth. But I can't just say some solutions and write down 3 particular ones and then say and so on and so forth. I need a general expression for what solutions look like, but that's easy to supply. Once again, we know the second coordinate has to be 2, and if we want a perfectly general expression for any old solution, well, you've known how to deal with this since Algebra 1. We don't just say some specific number, we introduce a symbol that could represent any real number. I will use t, for example, where t can be any real number. But whatever it is, once I introduce t, I know what the first coordinate, x, must be. It has no choice but to be 1 plus 3t. So rather than just writing down some solutions, we could say all solutions have this particular form. 1 plus 3t for the first coordinate, 2 for the second coordinate, and t for the third. So t is just functioning as a parameter here. It can take on any real number value, and that value determines the value of the first coordinate, the x coordinate. And when we wrote our underlying system in this form right here, after pushing everything that wasn't the leading variable over to the right, which in this case was just that 3z, we should recognize that this variable z is what we would call a free variable, which is why its value in my general expression for the solution here is just a parameter. It can be anything. It's free to be anything you like, unlike the other two cases. 2, the second coordinate, is obviously as fixed as anything could be, and the first coordinate, we've written it in such a way that it depends entirely on the value of the third coordinate. So we have our one free variable, z, and the 2 other variables. Now, what I've just written there, where I wrote all solutions, is one way of expressing all the solutions. But there are other, often much more useful ways of expressing the solutions. This way is nice if we just want to generate a lot of individual solutions, right? Let t be 1, let t be 2, let t be pi. They all give you solutions to the system. But hey, why not write the solutions in nice linear algebraic terms, in terms of vectors? So let's rewrite it. Each one of our solutions is a point x, y, z, or vector x, y, z. And of course, the components of that vector are 1 plus 3t, 2, and t, like so. And you might reasonably say, oh, come on, you haven't done anything except transpose this thing. You just wrote it as a column instead of a row. Big deal. Well, okay, you have a point, but I would counter that once we write it this way, it's a little easier to see how to decompose it further into a linear combination of 2 simpler vectors, like this. Hey, that's nice. Now I've got a constant vector plus all scalar multiples of some other constant vector. Well, I'll be damned. That takes us back several lectures to where we talked about lines, planes, and hyperplanes. Review that lecture if need be, or reread the relevant sections in the book, but you should recognize at once that this corresponds to a line in R3. Right? From the origin of R3, we're going to climb up this vector, which looks something like this, and then from its tip, we are going to add on scalar multiples of vector 3, 0, 1. When we add on all real multiples of that vector, we end up with a line in R3 as claimed. And every individual point on this line is a solution to the system of linear equations whose corresponding augmented matrix was reduced down to this form. So we have infinitely many solutions, a whole line's worth of them. And typically we would express those solutions in this form to emphasize the geometry, though of course writing it like this is fine too. Let's look at another example. Suppose we have a system of 3 linear equations in 3 unknowns, and after doing Gaussian elimination on the corresponding augmented matrix, we boil it down to this form. What can we say about the solutions of the system? Well, this turns out to be very straightforward on account of this bottom row, which corresponds to the equation 0 equals 7. So we don't even have to bother with the equations corresponding to the other rows, because the one corresponding to the last row clearly has no solutions. And if we can't satisfy that equation, then we obviously can't satisfy the entire system, which means that the system underlying our original augmented matrix has no solution. Or another way of saying the same thing, it's an inconsistent system. The moral of the story here is if you ever have a row that consists of all zeros on the left side of the bar and then some non-zero number on the right side of the bar, that corresponds to an equation that 0 is equal to some non-zero number, which obviously can't be satisfied, and that means your system has no solution. But let's consider another example, just like the previous one, except that here, where I had a non-zero number before, following all those zeros, let's put a 0, so that I have an entire row of zeros. What does this 0 row tell me? It's not a nonsense statement like before, because in isolation, this row is just telling us that 0 equals 0, which is, well, true. But this 0 row is telling us something about the underlying system. It's telling us that one of the equations, one of those constraints on what the solutions have to look like, is redundant. It tells us nothing new. It tells us that what ostensibly, before the row reduction, looked like a system of 3 linear equations and 3 unknowns, included one equation that wasn't actually doing any work, that was only imposing constraints on the solutions that had already been imposed by the earlier equations. And if we think about it that way, we might guess that our system of 3 equations and 3 unknowns, which normally we would think would have a unique solution, should, in this particular occasion, have infinitely many solutions. Because effectively, we really only have 2 equations in 3 unknowns that matter. And 2 equations in 3 unknowns, well, as we discussed in an earlier video, such systems typically have infinitely many solutions. So 0 rows are often hints that there are infinitely many solutions. Let's see exactly what they look like in this case by following the same basic process we used last time. Oh, first of all, I should note that this is indeed in reduced row echelon form. We have 2 pivots. There's obviously no pivot in the 0 row. And above and below our pivots, we have only zeros, and we have our little staircase with one wide stair at the bottom. But anyway, since we have this thing in reduced row echelon form, we should be able to get the solutions very quickly. To do so, let's extract the corresponding system of linear equations. And you might say, hey, what about 0 equals 0? I guess you could write it there if you want, but there's no point. I mean, to verify that some ordered triple, like say 2, 2, 1, satisfies the system, you'd pop the coordinates in the first equation and say, well, let's see. 2 plus 2 is 4. Yep, that checks out. And then pop the coordinates in the second equation. Let's see, 2 plus 3 is 5. Yep, that checks out. But nobody would stop to say, okay, 2, 2, 1. Well, is 0 still equal to 0? Of course 0 is still equal to 0. You don't even need to check that, so we don't even bother writing it down. But let's get back to the main proceedings so that you can see how to get all such solutions. Well, remember what we did in an earlier example. once we have achieved reduced row echelon form and we extract the corresponding system of equations, we then keep the leading variables, the ones that appear first, which will always have a coefficient of 1 since we are in reduced row echelon form, and we just shift everything else to the other side of the equation. To avoid a traffic jam over here, I'll just move them over like so. And let me tidy this up a little more. That's better. Well, this is nice and tidy, so we should be able to write down the complete solutions to the system, but it will help if we first notice that z is a free variable here. And please also notice, before we move on, that our free variable z corresponds to a column without a pivot. That's always the case. When we have a column with no pivot, a non-pivot column, then the corresponding variable will be free. And we will use that observation to come up with a quick way to write down solutions very soon. But it doesn't take much work to write down solutions at this point either. Let's see. Our solutions are points in R3 because we have three variables, x, y, and z. So our solutions, in general, we will just indicate by x, y, z. But let's be more specific. Let's start with our free variable, z. There's a solution out there where z is 19. There's another solution where z is negative 147.3. There's a solution for every value of the free variable z you could hope to see. So in our general solution, we'll just introduce a parameter t, where t can be any real number. And now we can just fill in x and y in terms of t, because of course both x and y depend on the free variable. Well, whatever we have for t, x is just going to be 4 minus double of that, and whatever we have for t, y is going to be 5 minus triple t. And in one sense, we're done. We have described all the solutions. We have a recipe for the solutions to this system. But let's do the usual thing and decompose this into a linear combination of simpler vectors, like so. I've just peeled off the constants and made a vector out of those. And then we have plus t times the constants associated with t in each component. And here too, we should immediately recognize what this represents geometrically. That is a line in R3. Maybe it's something like this. Every point on this line is a solution to the underlying system whose corresponding augmented matrix gets boiled down to this form in reduced row echelon form. And yes, our intuition was right. That row of zeros, which told us that one of our original equations in the system must have been redundant, and therefore that although we had a system of 3 equations and 3 unknowns, it would behave like a system of only 2 equations in 3 unknowns, and therefore we expected to have infinitely many solutions, and there indeed they are. So geometrically, you can imagine that whatever the original system looked like, before we turned it into an augmented matrix and slowly, perhaps through many steps, reduced it to this one, whatever that original system looked like, we had 3 linear equations and 3 unknowns. Each one had, as its graph, a plane in space. And we could imagine that the first 2 planes would have intersected in, of course, a line, namely this line. But then the third equation in that original system would have been redundant, a fact that was revealed algebraically by the appearance of this row of zeros when we do Gaussian elimination. That redundant equation, its graph would have been some other plane in space, and it would have had to be positioned in space in such a way that that third plane actually contained this line where the first 2 planes intersected. And because it contained that line, it didn't shave away the solution space. It was, in that sense, redundant. Okay, I think you get the point. Oh, actually, there is one last thing I want to say about this example before I get rid of it. I mentioned briefly in passing that there's a kind of shortcut, a quick way to go from reduced row echelon form to the solutions. Well, maybe not quite to here, but at least to here. And I'll show you what that is right away. I'll need some space, though. Okay, and let me rope all this stuff off. Let's just pretend it's not there for now. We've got our reduced row echelon form. How are we going to write down the solutions? Well, the first thing is to note that our solutions are going to have 3 components, right? 1 for each column. So let's go ahead and call our solutions vectors x, y, z, and now I'll need to write down what they look like. In this quick version, the thing to recognize is that z is going to be a free variable because it is a non-pivot column. Where we have pivots, we will have variables that are either constants or more likely depend on free variables, any variables that appear to their right in that row. But any column without a pivot corresponds to a variable that is free. So we know z is going to be free. So that being so, in this quick shortcut method, I'm going to go ahead and write a parameter in for z. T, that's my only non-pivot column, so that's my only parameter. We'll do some examples where we have multiple non-pivot columns and therefore multiple parameters. But once we've done that, we should be able to fill in the other slots very easily. Let's get x, which we can get from this first row right here. That first row tells us that x plus 2z is 4, or shoving the 2z over to the other side of the equation, x is 4 minus 2z. But we're using t as our parameter for the z variable, so we would say that x must be 4 minus 2t. Does that make sense? I hope so. Let's do it on this second one to get our expression for y in terms of t. Well, just in our heads, this thing is telling us that y plus 3z is 5. But we're thinking of z as t. We've assigned it that parameter. So push the 3t over to the other side, and we get that y is equal to 5 minus 3t. And hey, now we have expressions for the solutions. This thing works for all values of t. And of course, I can decompose that just as I did right here, like that. So I'll say it's this for all real t. And that's nice and neat, just going from there to there, basically in one step. I mean, there's the one step and then the decomposition, which is easy. We haven't really done anything differently than I did over here. It's just less to write down, but we are thinking in our heads about that important connection between free variables and non-pivot columns. So I will probably use this quick method in examples that follow so that you can get used to it. But don't forget what's going on underneath. Free variables correspond to non-pivot columns. And you should understand why. Don't just memorize that fact, though it is something you should know. It's because each row corresponds to an equation, and anything in a non-pivot column gets shoved over to the other side, where we recognize it as a free variable, and we assign it a parameter. All right, good. Let's do another example with a larger matrix. This one. Let's say this is the reduced row echelon form of the augmented matrix corresponding to some system of 4 equations in 4 unknowns. Well, if we hadn't looked at this matrix, we might expect there to be a unique solution, because there are as many equations as there are unknowns. But oh, now that we've seen this thing in reduced row echelon form, we have that snapshot of its skeleton, we have only our 2 pivots, but also these 2 non-pivot columns, which suggests that we will have 2 parameters in our solution set, because we have 2 free variables. If we call our variables x, y, z, and w, then y and w will be free. So what are the solutions to the underlying system? Well, we could, as we did originally, write down the equations, extract those equations, push all the non-leading variables to the other side, and then write down the solutions that way. Or we could do a lot of that work in our heads, as I just explained. Let's do that. I think you'll see it's pretty easy. For our solutions, we'll have vectors in R4, 4 components, 1 for each variable. And what will they look like? Well, y and w are going to be free variables. So let's assign them parameters. I'll call yt and ws. And they can take on any values we like. But once they have values assigned to them, then x and z will be completely determined. And we can see how by looking at this augmented matrix. Think of the first row as an equation. X plus 2y plus 3z is 7. Well, we shift all the stuff that's not leading, that's not the x, to the other side. Then we would have 7 minus 2y minus 3w. But we've assigned y and w the values t and s. So x is going to be 7 minus 2t minus 3s. And z, well, let's see. We have to go up to this equation, which is the only one involving z. That equation tells us that z plus 5w is 8. We'll shift the 5w over to the other side, and we get z is 8 minus 5w. But we have assigned the value s to the variable w. So this will be 8 minus 5s. And look at that, we've got it. But to understand it better geometrically, let's decompose it into a linear combination of simpler vectors, like so. So the solutions to our system are all vectors of this form, where t and s can be any real numbers. But geometrically, what is this? You should recognize it from that video on lines, planes, and hyperplanes you watched oh so recently. This is an ordinary 2-dimensional plane, but in R4. From the origin of R4, we step up on that vector, which I guess I'll put this in blue to do a little color coding. And then from that point, we are adding on linear combinations of these two vectors, which I'll try to continue with some color coding here. And if we're looking at all linear combinations of those vectors, we're getting some entire two-dimensional plane pervaded by the grid that those two vectors determine, which spreads out in R4. All the objects involved are things we can get our heads around. Vectors, which are one-dimensional objects, and here a plane, which is a two-dimensional creature. But it's all taking place in a four-dimensional space, which is why we have trouble making a very convincing drawing in R3, much less the two-dimensional tablet on which I'm drawing. But since all the pieces involved are of dimensions we can understand, we can still get a feel for what's going on, even if I can't draw the ambient space in which it all takes place. If you understood this example, I think you understand the basic idea. If we had been working with a gigantic augmented matrix in reduced row echelon form that had 9 non-pivot columns, then we would end up with 9 free variables, and therefore 9 parameters in our solution space. And it turns out, this is something we can prove, that the vectors being scaled by those 9 parameters, or however many parameters we might have in a similar situation, will always be linearly independent, just as these two vectors were linearly independent. And as a result, our hypothetical 9 vectors would sweep out a 9-dimensional hyperplane in whatever ambient space we're working in. So our solution space to that system of linear equations would be a 9-dimensional hyperplane. And that's the basic idea in a nutshell. Now, as you listen to that, you might reasonably ask, well, how do we know that those vectors attached to the parameters will always be linearly independent? I mean, couldn't there be some linear dependence there, in which case the solution space wouldn't be quite as big as we think? It's an excellent question. As I said, it does turn out that they will always be linearly independent, and it would be possible to explain that at this point, but I don't think the argument would be very illuminating. Whereas, if we wait just a little bit until the end of Chapter 4, when we've introduced notions like the image and kernel of a linear map, then we'll be able to understand why those vectors have to be linearly independent in a much more illuminating way, a way that will link up various ideas we've encountered throughout this chapter and help you see geometrically what's going on. So I will try to remember to come back to that topic when we reach the appropriate point. But for now, we have reached the end of this video. I will see you next time when we talk about inverse matrices. Until then, fare thee well.